We can hear the applause a little louder after the lunch, please.
Yeah. Good afternoon, everyone. When I asked Surojit about my time slot, he told he was this after lunch. So I know how it feels, right? After lunch, listening to CAT, Comchems and all. And Dr. Ramesh Sisla, just before he winded up his presentation, he told that his presentation is short, and I'm pretty sure I'm going to break your record now. So I'll be keeping it very short. And before I get into the presentation, I would like to thank Advent and Informatics and team, Surojit's team, to organize such an interactive session to meet with the industry leaders over here, both from industry and academia. So here just I would like to say some of the case studies where we have solved certain kind of problems in drug research, both in the small molecule and the antibody space. And as discussed by the previous speakers, so we use ICM in different facets of drug discovery, like start from the small molecule design to the large molecule biologics, the peptide dockings, peptide screenings, and the SAR analysis, and so on. So there are many case studies and many success stories that we can share, but considering the confidentiality thing, so I'm confining my presentation to one case study in small molecule, one in antibody design. So with that, so I will start my first case study on the virtual screening and binding. So here is a target of interest where we need to come up with a non-covalent inhibitor, right? And the challenge is the target exists in multiple isoforms. Like these days, many focus on dual inhibitor or selective inhibitor strategies. And adding to the complexity, we don't find any crystal structure reported in the structure, in the database. That's one more thing. So in all these cases, the first thing that we generally go with is conventional way of approach is we'll go with a sequence comparison, right? We do the sequence comparison, take from UniProt, compare the sequence, try to see. But that particular exercise didn't give us a proper results, because using homology modeling approach, we have built the models. Model is fine. The next step, we have predict the pockets, fine. But whatever sequence analysis that we are seeing is not correlating over there, because it's not only about the target but also with the off-target approach as well. You need to consider both. So if with such a kind of scenario, so we used ICM in each and every phase of this particular project, because there were challenges at different levels. The first, the homology modeling. So we even have the alpha fold structure. You can take the alpha fold. So when we are comparing the alpha fold versus homology, the pocket analysis couldn't give us a confidence that okay, we are getting the pocket for really good for the target, but what about the off targets, the other isoforms, are they reliable? So there were many questions coming into the picture while addressing this particular problem. So initially when we started with the ICM pocket finder, so basically to understand how the things go there, so we are able to find a kind of non-canonical pocket, let's say cryptic or a small kind of extension to the original pocket in the target, which is not there in the off target. So then the question is, can we target it? Even if we target it, whether the biology has the procedure to evaluate it, the question there. So after a series of iterations, we found okay, we can let's do a virtual screening. So for that virtual screening, we have used VLS cluster licenses of ICM. So we launched the study on cloud to find out what are the possible hits that are coming into the actual pocket, what are the possible hits that are coming in the newly found non-canonical or some kind of subtle pocket, which is looking like an extension of that original pocket. So finally we arrived at a set of hits that are actually binding at each specific pocket. Then started a series of iterations to find, can we build a molecule, can we make a molecule like this, or what are the functional groups over there, what could be the potential chemical group that can have a strong binding at the conventional pocket, what are the non-conventional amino acids, what are the amino acids in the non-conventional pocket, how can we have an interaction over there, can the molecule remain stable? So with all these questions, so initially we tried to come up with several designs. So it's some close to some 100 designs we tried around. So finally, what happened? So here you can see the prediction over here. Months after we developed an in silico model for the target of interest, there was a crystal structure reported. I mean, the structural biology team came up with a crystal structure with the molecule. So here, I mean, the pointer is not focusing. So, oh, sorry. So here you can clearly see the perfect overlay of the predicting mode. So the purple versus the yellow, that is, as you can see over here, the experimental versus the predicted. So the model that was built using the ICM for a target which is not actually deposited, have multiple isoforms, tricky pocket, though not sure whether to go with the conventional or the other one. So we are able to clearly map, design a molecule for that. And this research is still in progress. They are trying to improve the potency. So I'm not going to speak much about the IC50s and how we going further. But at the same time, again, there are several iterations happening around the cryptic pocket, not cryptic, like the non-conventional pocket that we found around. So at this juncture, we are further fine-tuning the hits that we observed, how can we further refine the interactions that are observed at the non-conventional pocket as such. So be it the pocket finder, and I must say the compatibility of the ICM licenses with the cloud is really remarkable. So literally you can use all the close to all 1,000 licenses perfectly used for your study that can give you a perfect interaction. So this is one study that I would like to highlight in the small molecule space. So if you have any questions here, I'm happy to take.
So the cryptic model which you predicted from model, and the cryptic side you predicted from the experimental structure, did they match?
Yes. Yes, actually within that we have the non-conventional site as well. Yeah. So that is how the binding mode is accurately predicted using the computational tools, and we are able to build the confidence to the project team as well, that the model is perfect. So whatever designed so far, you can go ahead and do the next steps. So now that once the model is validated, then right now it's a little straightforward thing that to approach for any structure-based projects. Yeah.
One question. So when you predict the different pockets using ICM pocket finder, find the number of possibilities it will throw out.
Yes.
So how do you select which should be the best pocket to target? Is it only based on scores or?
Perfect. So we will get DLID scores in ICM. We didn't go along only with the DLID scores. So basically the approach is we evaluated how many hydrophilic amino acids. I don't want the pocket to be more hydrophilic amino acids, because you need to have more polar groups over there, and it will affect the admit there in the next steps, though you get the docking scores very well. So that is one of the prime criteria that we consider to analyze the pockets. Not all scores are one aspect, the other is looking whether it is whether the non-canonical pocket that we are observing is worth investing, worth looking for. What is the milieu surrounding residues? Is there any pocket, and how the pocket is changing, probability and all. Yeah, that's how. Yeah. So this is one of the case studies that I would like to discuss about the small molecule drug design.
So even across isoforms, is the binding state unaltered? So even across isoforms, did you see that the binding state of the compounds is unaltered?
Yes. The off targets won't have that non-canonical pocket. So whatever the predictions that we got from ICM are holding true there.
So this is isoform specific targeting?
Yes. Yes. And moving to my next case study that I want to discuss is antibody modeling. So here is an interesting case study. So the objective is we have an antibody in the market which is established and all, but we want to come up with some surrogates with some improved properties. So the critical challenge over here is, again, even in this case, the target of interest crystal structure is not properly elucidated. You don't have the complete crystal structure. That's one more thing. And the second concern is the activity should not last. It's not about the activity, but but the main concern over there is to have a proper isoelectric pH. They want to improve the isoelectric pH of that particular antibody. So this was a major challenge. If you change the any property, even if a single amino acid changes in an antibody, the entire binding pattern may change. So this is a really challenging thing, and we don't have any information of epitope-paratope interactions because the target of our interest has a poor resolution at one end. So we cannot rely on it. I mean, it's not completely elucidated. So that was the challenge in this project, and so it all started with a similar approach. We went with the homology modeling, build the model, that's fine. Then the trickiest part comes in the next step. So we have the antibody structure, we can dock it. Then we need to sort out the structures in such a way how to find a proper epitope-paratope interface with a limited literature evidence over there. So one approach we took is, when it comes to antibody modeling, we have to think few steps ahead. For example, what happens when the antibody that we are suggesting as a modeler goes into the lab? The first problem the biology may tell us is expression concerns. Next concern, aggregation, right? You need to keep all these things into consideration and yet design a molecule that should not lose its binding affinity, yet the isoelectric pH should change. So basically the requirement is to have isoelectric pH in two buckets, range X, range Y. And again, the challenge is to have two buckets of PA, not even one bucket. So if that is the case, so the challenge kept on increasing. So initially we started with the docking studies to understand the epitope-paratope interface. So during that process, so we used a set of tools like, see, in the previous case we have used pocket finder, like a small molecule drug discovery, right? But you cannot compare a pocket of an inhibitor with an antigen-antibody binding, because antigen-antibody binding will be a flat surface. It's not like a cavity that you observe. And the DLID score principle won't apply in this case, not much. So then, though we have done the pocket analysis just to find the pockets where they are and kind of analysis to get an idea, then the next topic of interest is to visually identify where are the hydrophobic patches. Okay, so where are the hydrophobic patches, and where are the hydrophobic patches of your antibody, where are the hydrophobic patches of your antigen. So that will be a plausible chance of repulsion, right? Though in pocket finder you may find something biased kind of observation, it's going to be like that. And second most crucial factor is your electrostatic potential, right? So that plays a crucial role in binding. So we evaluated the electrostatic potential of antigen versus antibody, and in this way there were a series of possible epitope-paratope interactions that we shortlisted. So this could be possibility 1, this could be possibility 2. We took the binding scores also into consideration. What are the possible binding scores ranking in this kind of orientation, the other orientation and all. So after this kind of repetitive analysis, so we finally figured out few promising epitope-paratope poses and the interactions. And then the next question starts, which part to mutate to improve the PI. So initially we have used the mutational scanning in ICM tool. We have a tool there to analyze across all the amino acids to find which could be a possible change that can happen. It's based on the Monte Carlo approximation that we can do that. But there what happened, fewer considerations are okay, but because here in this case there are some overlapping observations that we are getting at different poses, different changes and all. So we thought of again checking it manually, because we don't want to simply go with aromatic to aromatic change. It should not be the same making tyrosine to phenylalanine. That's not the change that we are looking, because it's the active. If you do a simple switch with tyrosine to phenylalanine, the activity might be retained, the binding affinity will retain. But what about the PI? No guarantee. And you should not increase the hydrophobicity of the molecule as well, because in the next step definitely it will aggregate, the expression will fail. So with these things, so it was tricky to identify what are the possible mutational spots. So we done the computational scanning for all the amino acids to see which is the most favorable change. Then we try to modify them according to the electrostatic potentials that we observe. So in the previous step I mentioned, to understand the epitope-paratope interface, we analyzed the electrostatic potential. So combining that information from the Monte Carlo observation that we got, so we finally identified few interactions, few changes over the antibody that can be leveraged to improve the isoelectric pH. But the game didn't stop there. It ended up with close to 2 lakh sequences possibility. So it can be of any combination, either single mutation, 2 mutations, 3 mutations, 4 mutations. If you list down the number, it will go to like a lot. So then we took the support, we worked along with the mathematical modeling team to understand, to shortlist the sequences, and we took the help of omics teams, multi-omics teams to understand as per the conservation rules. What are the conserved things across a homologous protein or any of the target of interest sequences and things like that. And finally, we narrowed down to 60 sequences. 60 sequences with 30 sequences in each bucket, X bucket, Y bucket. So this finally we told the biological team that this is the one that you can focus on. These sequences, these mutations you can do. They have a very little chance of hydrophobicity aggregation issues. So finally they chose one bucket, the range of 7 to 7.5 bucket they chose. They want to go with it. And once the results are out, so it's really interesting to see. As you can see here, the reference over here is at around 6.5, the reference antibody isoelectric pH. And if you see the 7 to 7, there is only one outlier in the designs that the CAD team proposed. And the majority of them fall in the particular bucket range, and they are expressing. So this study is also in the next phase, the expression wise hydrophobicity. And one more important thing with the antibody is immunogenicity, right? It should not induce any kind of immunogenic response. And with the data that I am getting, that they are not so reactive. I mean, they are not inducing any immunogenicity response as well. So it's the same set of tools that we have in ICM, so but a different approach that we try to stabilize a particular antibody research. So any questions here, I'm happy to answer.
Thank you very much. So, when you're modeling antibodies, are you modeling only the Fab region or the entire staff includes the region as well? And if it is only the Fab region, then how you are ensuring the stability of the disulfide bond between the light chain and the heavy chain?
Yeah. So it's the Fab. We are not going with the FC and all. The main thing is coming up with the proper information of epitope paratope, so that because here in this case for this objective, the binding affinity should not change, so the interactions should not be changed. That's one thing. So disulfide, whatever interactions residues that are contributed for disulfide, that we kept constant. So we are not disturbing the other factors there.
You were saying that you were doing a homology model.
Yes.
Now, if you are kind of designing an antibody that is kind of sequence is similar to the template, then maybe you can ensure that disulfide bond will also be in the same place. But if you are kind of trying to design a kind of very novel antibody,
then it's a challenging thing. So here it's a surrogate design. That's number one, and the challenge is with the physical-chemical properties. Yeah.
So immunogenicity, do you have a model? Predicting immunogenicity?
Yeah. Have that.
Thank you.
Thanks.
Any other questions?
And Ramesh sir, I broke your record.
Let's give Dr. Srinivas a big round of applause for such an informative session.
Thank you.